Hi there, this video is your introduction to angular momentum. So before you continue on with this video, you should, if you have not already, go take a look at the YouTube video link that is presented here. This will be also provided for you on Canvas for you to get the direct link. It's an entertaining video that walks through some of the different components you want to think about with angular momentum. Okay, so when you're finished viewing that video, come back here and we'll continue on with our angular momentum discussion. Okay, so hopefully you are finished watching the video now. So as you know, angular momentum becomes important whenever we're talking about a rotating body. And since in our quantum mechanical adventure, we're starting to talk about spherical systems, rigid rotors. Soon we'll be talking about the hydrogen atom, where we have electrons rotating around a nucleus. Okay, we're starting to get into the realm of rotating bodies. So angular momentum is now going to be an important consideration for us. Okay, so we have already encountered the angular momentum previously in our discussion, so hopefully you remember that our Hamiltonian for the rigid rotor is related to the total angular momentum squared operator, so L squared. So be careful there, total angular momentum squared, not just the angular momentum. Okay, so if we think back to our rigid rotor Hamiltonian, remember that was just composed of a kinetic energy term. We assumed that there was no potential energy in our model. Okay, and then we said that that kinetic energy term could be modeled by our total angular momentum squared over 2 times the moment of inertia, or 2 mu r squared. Okay, so we've already seen that the spherical harmonics are solutions to the rigid rotor Hamiltonian. Okay, and then that means that they should also be wave functions of L squared. Okay, since this 2 mu r squared over here in our Hamiltonian is just a constant, okay, then they should also be wave functions of our L squared operator. And here is just a reminder of what our spherical harmonics look like. Okay, so we've seen this table of our spherical harmonics before. Okay, remember you have to be careful what your different L and M sub L values are, so you get the right function to work with. And then these are the various 3D polar plots of those spherical harmonic functions. Okay, so here you'll start to see your familiar S-shape orbital, P-shape orbital. This is your dz squared orbital. So you can start to see some of those familiar shapes that you've encountered in some of your other classes. We'll see these again when we start talking about the hydrogen atom and our orbitals, but for now, just a reminder of what your spherical harmonics look like. All right, so let's take a closer look at our quantum mechanical operator for the total angular momentum squared. This is one of the operators in the table on your appendix that you'll have access to, so no need to memorize this for your purposes. We see that we have, remember, functions of theta and phi contained in this total angular momentum squared operator. Okay, so we just said that the spherical harmonics are eigenfunctions of our total angular momentum squared operator. So what does that mean for us? Well, it means that we already know what our eigenvalues are. Okay, so we just talked about how this is related to our Hamiltonian for the rigid rotor model. Okay, so there's just a constant out front. So when we take that analogy to our eigenvalues, okay, we should see that we get out eigenvalues for a total angular momentum squared operator that are very similar to our rigid rotor eigenvalues. Okay, so we're just essentially missing that over 2i component that we had for the rigid rotor energy levels. Okay, so remember for E sub j was h bar squared j times j plus 1 over 2I. Okay, so just taking that angular momentum part of the expression from the rigid rotor, okay, and then just remember that for our purposes, J is the same as L, okay, so remember that's spectroscopy, and this is when we're talking about angular momentum or your hydrogen atom. Okay, so we know that our eigenvalues of our total angular momentum squared operator are h bar squared L times L plus 1, where L can range from 0 to infinity at this point. Okay, so that was the total angular momentum squared component. We can look at also the individual components of our angular momentum. So if you remember from physics, you know that you have x, y, and z components to your angular momentum in a three-dimensional space. Okay, so we can use our conversion here to obtain our different components of the angular momentum. So as a reminder for how to obtain those, if you're rusty on your matrix algebra, if we want the x component, you're going to basically cross out those two lines, okay? And then you're going to take the cross product of what's left. So that leaves us with y pz, which we have here, and then the other cross product of z py, which we get here. And then you would go through and do that same process for the other two components. Okay, so we, working now in a spherical system, of course, are going to want to translate this into spherical coordinates rather than working in the Cartesian coordinates. So all we have to do is plug in our quantum mechanical operator for our momentum, okay, which we've done here in our Cartesian coordinates, okay, and then just do our conversion to our spherical coordinates over here. Okay, so these are all equivalent, so left side and right side are, again, all equivalent options for working with the different components of your angular momentum. It just depends on what kind of system you're working with. That will determine which one is going to be easier for you to work with. Again, since we're in spherical, working with spherical systems right now, we're going to stick with our spherical coordinate system. All right, so let's ask ourselves for a moment, which one of those components of angular momentum would you like to work with? I don't know about you, but I am liking the looks of this one right there. Okay, nice and simple. All right, so it turns out that it doesn't matter which one we work with. We just want to pick one for our purposes going forward. And chemists that have come before you have, in fact, decided to take the easy way out and pick the simplest component to work with. So our lives now will revolve around the z component of the angular momentum. All right, let's play around with LZ. Okay, so we already know the spherical harmonics are eigenfunctions of the total angular momentum squared operator. Well, it turns out that they are also eigenfunctions of the LZ operator. So remember from before, this is our z component of the angular momentum, our quantum mechanical operator for LZ. And I want you to take a minute, so pause the video right now. I'd like you to take a minute to show that e to the im phi is an eigenfunction of LZ. Okay, so let's do a practice eigenvalue problem right now. So pause the video, take a minute to evaluate LZ acting on e to the im phi. Okay, so hopefully you have taken the time to work through that exercise. So let's see how you did. So we're going to evaluate this eigenvalue problem. Okay, so let's plug in our quantum mechanical operator corresponding to LZ, and it's going to act on our function. Okay, so then we get minus I h bar times Im e to the Im phi back out. Okay, so looking at our coefficients out front, we have minus I times I, which is going to give us a positive 1. Okay, and then we're left with MH as constants as well. So we get positive MH bar e to the Im phi. Okay, so question for you now is, can you identify what the eigenvalue is? So this is a pop quiz for your material from earlier on in the semester. So what's our eigenvalue for LZ acting on e to the Im phi? Well, it is this part, right? So remember, eigenfunction gets spit back out at you. So that is the e to the Im phi. And your eigenvalue is the constant out front. Okay, your next task is going to be to take it a step further and show that our phi component of our spherical harmonics, phi of phi equals 1 over square root of 2 pi e to the Im phi, is also an eigenfunction of LZ. Okay, so pause the video, take a minute to evaluate this, and we'll meet back in a minute. Okay, hopefully you have now an answer for this question, so let's take a look and see what we end up with. So we have LZ acting on our function. Okay, so remember LZ minus IH bar d phi, and then pop in your function. And hopefully you realize that this is just the same thing we did up above, except we just have this new constant out front. So this is not actually going to change anything in terms of how d phi acts on our function. So we're essentially going to have this same result pop back out, except we're going to have an additional 1 over square root of 2 pi that tags along with it. Okay, so we end up with mh bar 1 over square root of 2 pi e to the Im phi. Okay, so now let's ask ourselves, what are the eigenvalues and eigenfunctions for this situation? Okay, so be careful not to go on autopilot here and just bring out all of the constants as your eigenvalue, because remember, the eigenfunction is the part that gets spit back out at you. Okay, so if this is our eigenfunction, we're looking to get that whole thing back out. Okay, so this part right here is the eigenfunction. All right, so a little extra on there. Okay, and then that leaves mh bar again as our eigenvalue. All right, so just be careful. Sometimes students like to just look at all the constants that are out front of a function and include that 1 over 2 pi. Okay, but remember, this belongs with your original function. Okay, so we have just shown that the phi components of our spherical harmonics are eigenfunctions of LZ. Okay, and just remember here, remember from our video on the spherical harmonics, these m values will range 0, plus or minus 1, plus or minus 2, and so on. Okay, so now let's take it to our final step of showing that the spherical harmonics, the full spherical harmonics, are eigenfunctions of LZ. Okay, so just keep in mind here that since LZ only acts on phi and not theta, you can hopefully just see by inspection that the spherical harmonics are eigenfunctions of LZ. Okay, so and put this together, have LZ act on our full spherical harmonics, y of theta and phi. Okay, so I'm just breaking your spherical harmonics up into the different components. Remember, we have our normalization constant here, and then our associated Legendre functions, okay, are coming out right here. So remember, LZ only acts on the phi component of our spherical harmonics. Okay, so I've just brought out our normalization constant, and then the theta and phi components are coming after the LZ operator. Okay, but LZ, remember, is only going to operate on the phi component of our function. Okay, so that means that we can bring all of this out front, so none of this is going to be affected by our LZ. Okay, so constant, theta component, none of that is getting acted on or getting changed by that d phi part of our LZ. Okay, so we put in our LZ operator minus IH bar d phi. It's going to act on the phi component, that e to the im phi function. And then we get out, once again, if you take a minute to evaluate that, remember we just did that in our previous exercises, right? We get out our eigenvalue again of mh bar. Okay, so hopefully you can see a pattern here where the eigenvalues of LZ, whether you're acting on just the phi component or the full spherical harmonics, are going to give you the same result, okay, because LZ, remember, only acting on the phi component. Okay, so mh bar is the eigenvalue of our LZ component. So we could write that as an eigenvalue equation, if you like. So we can say LZ acting on our spherical harmonics is going to be equal to mh bar y, oops, erase. Okay, so there's our eigenvalue equation. If you want to put that together, okay, or we can just look at the magnitude of our resulting observable and say that LZ equals mh bar. Okay, so this would be the magnitude of the observable z component of our angular momentum. Okay, so just notice the differences there in those two equations. This is our operator. Operator has a little hat acting on our function, okay, spitting out our eigenvalue and our original function back out. That's the definition of an eigenvalue equation, okay, or we can just say the magnitude, the observable that we get out for the z component of our angular momentum is our eigenvalue mh bar. Okay, so one of the neat things about L squared, our total angular momentum squared operator, and LZ, the z component of our angular momentum operator, is that they share a set of eigenfunctions. Okay, so we just saw that the spherical harmonics are eigenfunctions of both L squared and LZ. Okay, so if two operators share the same set of eigenfunctions, then they necessarily commute. Okay, so then we can essentially write this relationship, which should look familiar. That's our commutator. Okay, so if you do a calculation of a commutator for L squared and LZ, you should find that they commute. Okay, it turns out that Lx and Ly, the other components of the angular momentum, also commute with the total angular momentum squared operator. Okay, so you would have a similar kind of situation for those. So these are all your commutator relationships here. Okay, but what's interesting is that the individual components do not commute with each other. So Lx and Ly don't commute with each other. Lx and Lz don't commute with each other. Lz and Ly, I think that's the third combo, don't commute with each other. Okay, so then we get these expression for those commutators of the individual components of the angular momentum that are not zero. Okay, so these do not commute. Okay, so what does that mean for us? Why do we care about commutating operators? Well, remember it said something about how we can measure them. Okay, so remember, if two operators commute, then we can measure their precise values simultaneously. Okay, so we can measure precise values for the total angular momentum squared and any one of Lz, Lx, or Ly. Okay, we can know those two components. But once we pick one of these to know Lz, Lx, or Ly, then by definition we cannot know the other two. Okay, so you pick one to know, and then you can't know the other two. Okay, so by convention, we tend to work, like I said, with the Lz operator. Okay, so this is the relationship that we're going to tend to focus on for our quantum mechanical applications. Okay, we could do just as correctly focus on these relationships. Okay, it's just that if you remember back to the functions that are associated with all of those components of the angular momentum, it's the Lz operator that's the simplest, and honestly that's the only reason that we focus on using Lz rather than the other two components. Okay, so moral of the story is we can know L squared and one, but not all, of Z, X, or Y component.